All right. All right, so again, we've talked about position and velocity. Now what happens if the velocity is changing? Okay, so this is what we want, right? We want the velocity to change with time. So how can this happen? Think about it. How can that happen? Well, I want you to consider your car or your bicycle. I don't care. How can you change the velocity of a car or the velocity of a bicycle? Well, I think let's just talk about the car. Okay, so if you change the speed, how do you change the speed? Simple, right? You can use the gas pedal, you can use the brake, but wait a minute, this is velocity, it's not just speed. Velocity is speed and direction. How do you change the direction? Steering wheel. So there's three ways to change the velocity in a car. Brake, gas pedal, wheel. So really there are three, all right? Three. Okay, now we're not going to talk about direction today, we're just going to talk about the speed, so the gas pedal and the brake. Okay, so here's the equation for average acceleration. You have to know this. So average acceleration is delta v over delta t. It's a vector. All right? That's all it is. So that means that your steering wheel in a car is actually an accelerator, right? Your gas pedal is an accelerator, your brake is an accelerator, and your steering wheel is an accelerator because it can accelerate the car, change the velocity. So here's a couple examples. So this is, you just drop a ball. This is really dirty. So you just drop a ball, right? What happens? It gets faster and faster and faster. So this is the motion diagram, you know. You can see that the distance gets greater and greater. And so the direction of the velocity is this way, and the acceleration is this way, okay? Because the velocity is getting larger and larger and larger. So that's the direction of the acceleration. Right? Acceleration always points in the direction of how it gets larger and larger. Right? So that's dropping a ball. Now here, we're throwing the ball up. And we're just concerned with the motion up. So what happens? Well, it slows down. So that's large, and it's less and less and less. Okay, so we're throwing it up, so the velocity is up, but the acceleration is still down. Because remember, the acceleration always, that's what's great about these motion diagrams. You can see that, you know, here's small, it gets bigger, bigger, bigger. So the acceleration is in that direction. Okay? All right. Now, here's a position versus time graph. These dotted lines are to help us. And here's a velocity versus time graph. Let's see if they make sense. So here, positive velocity, constant. So positive velocity and constant. Here, negative slope, so negative velocity, constant. Negative velocity, constant. Here, the slope's getting smaller, 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 smaller. Or positive, smaller, smaller, smaller. Slope is 0. Then it starts getting faster, 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 but negative. All right, so smaller, 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 0, faster, faster, faster. Okay, now what I'd like you to do, just use what you've learned, and please draw the acceleration versus time graph. And, you know, use these lines to guide you. So pause your video and do that, please. Okay, what's the slope of this? 0. So the acceleration is 0, right? The acceleration is the change in velocity. Is the velocity changing here? No. So the acceleration is 0. Over here, does the velocity change? No. Horizontal line, slope is 0. Acceleration is 0. Here, the slope, right, delta v over delta t, which is acceleration, the slope is constant, and it's negative. So the acceleration here, between this point and this point, it's negative and constant. So make sure you understand that. All right. I'm going to ask you 3 questions now, so just, you know, pause your video and make sure you understand these things. Okay, so this is a motion diagram. You've seen this before. Chapter 1. What is the acceleration of A? So pause your video. All right. So this is the motion diagram for uniform motion, right? Constant speed. So is the velocity changing? No. So therefore, what's the direction? There is no direction because the acceleration is 0. All right, here, you've seen this before in chapter 1. What's the direction of A? So pause your video and figure it out. Okay, we're back. Here, remember the acceleration always points in the direction of increasing distance. So here, this is small, bigger, bigger. So the acceleration points to the right. Okay, acceleration points to the right. And as you remember from chapter 1, this is increasing speed. All right, one more. So what's the direction of the acceleration? The acceleration points in the direction of the increasing distance. So what's it going to point? So here's small, it gets bigger, it gets bigger. So what's the direction of the acceleration? To the left. That's really important, by the way. That's why I'm making a big deal about it. All right, now we're going to do, okay, everybody read that and answer it. So pause your video. All right, we're back. The average acceleration of a movement, so here's the equation for acceleration, right? Acceleration delta v over delta t. So the average acceleration of a moving object is positive. So the object's speed is what? So you figure that out. Well, actually, there's not enough information to decide. If you only know the sign, positive or negative, of the acceleration, you don't know if something's going faster or slower. Now that's usually very confusing to most people, so we're going to explain this in gory detail. All right. So, again, we're always going to use this until I tell you otherwise. We're always going to assume that right is positive, left is negative. Okay, so here we have an object moving to the right, and you can see, all right, so the velocity is positive because it's moving to the right. And as I just said a few minutes ago, this is small, it gets longer, longer, longer. So the acceleration points to the right. If it points to the right, it's positive. So the velocity is positive, and the acceleration is positive. Now, is the speed increasing or decreasing? Well, you learned that in chapter 1. The speed is obviously increasing. Okay? So here's the important thing. This is a situation where we have positive acceleration, and we have the speed increasing. So remember that. Positive acceleration, increasing speed. Now, look at this. Okay, the object's moving to the left, so the velocity is negative. And again, the acceleration points in the direction where these things get larger. So the acceleration points to the left. And what's happening to the speed? The speed, is the object getting faster or slower? Faster. All right, so for the previous one, we had positive acceleration, increasing speed. Now we have negative acceleration, increasing speed. So, if you only know the acceleration, what do you know? Not a whole lot. All right, so the sign of acceleration doesn't tell you if you're going faster or slower. Okay, let's keep going. All right, this guy is moving to the right, positive velocity. The distance increases to the left, negative acceleration, right? Acceleration points that direction. What's happening to the speed? Increasing or decreasing? Decreasing. Decreasing speed, okay? So we have negative acceleration, decreasing speed. Next one. The object's moving to the left, velocity is negative. This is increasing, the distance is increasing to the right, positive acceleration. Is the thing going faster or slower? Slower! So, all right, so let's review. So this one we had decreasing speed, negative acceleration. This time we have decreasing speed, positive acceleration. So once again, the sign of A doesn't tell you anything. It doesn't tell you if the thing is going faster or slower. So what do you think? what else besides acceleration do we need to figure out if something's going faster or slower? Velocity. Velocity. So look, here, velocity and acceleration both have the same sign. They're both positive. When that happens, we have increasing speed. Look at here, they have the same sign, right? They're both negative. When velocity and acceleration have the same speed, increasing speed. On the other hand, when the velocity and acceleration have opposite signs or opposite directions, because sign is direction, right? If they have opposite directions, you always have decreasing speed. And the same thing, right? So opposite signs, decreasing speed. So we're going to use this throughout the entire semester, so you want to remember it, okay? So here's a question. So read it, pause your video, and figure it out. Okay, so this is a situation. The object's moving to the left. That means that's negative velocity. And the distance is increasing to the left, so the acceleration also points to the left. So the velocity and the acceleration both point to the left. If they have the same sign, which they do here, we know that the speed is increasing. And you just look at it. Isn't the speed increasing? Sure is. Here's the start. So here, then this is more distance. All right? So, okay? And again, what are the signs of A and V? They're both negative. So they have the same sign. They're both negative, so the speed is increasing. So again, this usually gives students a lot of trouble. So make sure you go through this and understand it, because we're going to use it a lot. Okay, now we want to talk about we're going to finally do some word problems, which means we have to learn the kinematic equations. So these are the kinematic equations for constant acceleration. That's all we're ever going to do in Physics 105, for a while anyway. All right, so kinematic equations for constant acceleration. So you have to really be careful of the signs. And again, this delta x, that's the displacement. So if you go in a circle and you end up at the start, the displacement is 0, like we talked about in Chapter 1. So you have to memorize these. So on the exams, I'm going to give you all of the equations that you'll need, except for the kinematic equations. And there's a reason. So these are the kinematic equations for one dimension. Later on, we're going to do kinematics for 2 dimensions. If you memorize these 3, then the kinematic equations for 2 dimensions are going to be like easy, free. Then later on, we're going to do circular motion. And if you understand these, you'll understand those. And so memorize these, all right? You have to memorize these. These will not be given on the exams. And you'll thank me later on that I forced you to memorize these things, okay? All right, but again, these are only true for constant acceleration, okay? So I want to do an example of constant acceleration, right? An example of constant acceleration. So the example I want to discuss is called free fall. And this is really important. You're going to have, either 1 or 2 labs. We're going to talk about this a lot. When we do 2-dimensional motion, we'll talk about free fall. So free fall is a big deal in introductory physics. So what's free fall? So free fall is motion where the only important force is gravity, okay? The only important force is gravity. So let's do some examples. All right, so if I'm in this room and I have a ball and I drop it. Now, there's no wind in this room. I'm not dropping it a very long distance or anything like that. So basically, what's the only force acting on the ball? Gravity. What am I ignoring? Air resistance. Is that okay for a ball in this room? Yeah, no problem. So this is free fall. How about this? Now, is air resistance important here? Yeah. So is that free fall? No. So you have to, you got to use your head when you think about it. Okay. I don't know how you're going to do this, Sully, but do your best. Okay, so I'm going to take this ball. I got to be careful. There's a lot of things I can wreck around here. Okay, I'm going to throw the ball. Now, here's the question. I'll be back. Okay, here's the question. After the ball left my hand and before it hit the wall, was that free fall? Think about it. After the ball left my hand, what's the only force acting on it? Gravity. It's free fall, right? Okay, how about this? Okay, after the ball left my hand and before it hit the floor, was that free fall? Well, once again, after it left my hand, what's the only force acting on it? Gravity. So it's free fall. All right, I can't do it here. I can do it in K132, but I can't do it here. What I'd like to do is throw the ball up. But if I do that, I'll wreck the ceiling, so I'm not going to. Okay, so basically, you know, I can take this ball and I can throw it however I want. And as soon as that ball leaves my hand, I don't exert a force on it. As soon as it leaves my hand, the only force acting on it is gravity. And so these are all examples of free fall. All right, here we go. Now, I don't know if this is true. I'm sorry. I got it on the web, but it's still, I mean, it's interesting. So let's pretend we're in New York City, where we don't want to be now for sure. So we're in New York City on the top of the Empire State Building, and we drop a penny. So according to this website, if you include air, the penny will be going 25 miles an hour when it reaches the ground. And the website said that's painless. I don't know about that, but whatever. If you can ignore air resistance, the penny will be going 210 miles an hour, which, you know, if the penny's going like this, you know, edge on, it will certainly break your skin. So again, I don't know if these numbers are correct, but is that free fall? I mean, if you get to the top of Empire State Building and drop a penny, is that free fall? No, right? Because air certainly plays an important role, okay? So, all right. So again, you know, when you have a homework question or a test question or something like that, you just have to read the question. And, you know, if they want to include air resistance, they'll tell you. If they don't want to include the air resistance, they won't say anything about air. So don't worry about it. In fact, we're not even going to talk about air resistance for quite a while. So for quite a while, we're going to just totally ignore air resistance. And it's fine. It's okay, you know. Like I said, if I'm in a room or if I'm like 2 stories up or something like that, air resistance is nothing or negligible. Okay. Now, okay, we're still talking about free fall. Okay, so the question is, you know, gravity is the only force acting on it. And it's a constant force. We'll talk about that, all right, sometime. And so what is the acceleration of an object due to Earth's gravity? So the acceleration in the y direction due to Earth's gravity is 9.8 meters per second squared down. Right? So that's the acceleration due to Earth's gravity. So what that means is you can go anywhere on the Earth as long as you're near the surface of the Earth, and you can drop something and measure the acceleration, and that's what it'll be. Now this is an approximation, you know. This is assuming that the Earth is a perfectly uniform sphere, which it is not, correct? So this is just an average value. Now, this is true, but we don't like it. What we want to use is this. So what we're going to say that a sub y equals minus g, which is minus 9.8 meters per second squared. All right, so why do we put a g? Because we get sick and tired of writing a sub y. Because, you know, a lot of the problems we're going to deal with Earth's gravity. So the acceleration due to the Earth's gravity, we're going to call small g. Why is there a minus sign? Well, because, you know, we're assuming up is positive, down is negative. Okay? So in our equations, which you'll see in a few minutes, we're not going to write a sub y when we're talking about free fall. When we're talking about free fall, we're not going to use a sub y. We're going to use minus g. Now notice, minus g equals minus 9.8 meters per second squared. So what's g? So g is positive 9.8 meters per second squared. so many students get mixed up with that, right? G is a positive quantity, okay? It's a positive quantity. G is positive. Don't forget that. All right. Okay, so, all right, so here are the kinematic equations for constant acceleration. One-dimensional motion. So I put x in here, you know, because I'm assuming things are going in the x direction. Well, let's just assume things are going in the y direction. Whoopee, who cares? So instead of having an x, you put a y. Big deal. All right, so you just replace all these x's with a y. Now, let's say we're talking about free fall. Well, just like I just explained, for free fall, a sub y equals minus g. So everywhere you see a sub y, you put a minus g. There you go. All right? So, if you know these three, which you're supposed to, then these are free, right? Because all you're doing is you're substituting, you're replacing the x's with y's, and you're replacing the a's with minus g. So these are called the free fall equations, okay, for vertical motion. You'll use them a lot. You wait until you see your homework. All right, let's do an example. We'll spend a lot of time on this example. Shucks. Okay, so here's an example. So it's a free fall example. So we're going to take a ball, and we're going to throw it straight up outside in a large room so we don't have the low-hanging ceiling, all right? And we're going to keep it simple, okay? We're going to say that a sub y equals minus g is minus 10 meters per second squared. So forget about the 9.8, just for this example, all right? We're going to say it's minus 10. Now, hold on a second. Let me write, what's acceleration? Acceleration is the change in velocity over the change in time. So let's write this a little bit differently. Let's say it's minus, oops, positive, sorry. No, yeah. Minus 10 meters per second. Now that's right, because a meter per second is a meter per second squared. But this is a cool way to write it. Because what does it mean? Remember, this is delta V over delta T. So what does it mean? It means when you drop something or throw something, you know, if it's free fall, it means that the velocity is changing by negative 10 meters per second every single second. That's what it means, okay? The velocity is changing by minus 10 meters per second every single second. So let's talk about this. So let's just say, I'm just making this up, let's just say we throw the ball and the initial velocity is 30 meters per second, okay? All right, so I'm going to make a table. Oh, I didn't make, whatever, who cares? Went a little crazy, that's all right. All right. Okay, so we know at time equals 0, yeah. All right, okay, so here, that means time equals 0, the initial velocity. So this is going to be time equals 1 second, 2, 3, 4, 5, 6. Okay, all right. Now, it's going at 30 meters per second up initially. Time equals 0. So, what is the velocity 1 second later? So you figure it out. You pause your video and you figure it out, please. And use this. Okay, so we're back. All right, so if it's going 30 meters per second, and the velocity is changing by minus 10 meters per second every second, 1 second later, it's going to be going 20. All right, how fast is it going to be going 2 seconds later? Well, again, it's changing by minus 10 meters per second every second, so it's going to be going 10. 3 seconds, 0. All right, so we're slowing down, then we're stopping, right? At 3 seconds, it stops. And then what does it do? Turns around, starts going faster, 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 faster. So 4 seconds, minus 10 meters per second. 5 seconds minus 20 meters per second. 6 seconds minus 30 meters per second. So this is on the way up, then it stops, then it's on the way down. And you notice how this changed by minus 10 meters per second every single second, right? Minus 10, minus 10, minus 10, minus 10, minus 10. Okay? Okay, now what I want you to do is, as soon as I stop talking, pause the video, use this data to draw a velocity versus time graph. By the way, I should have told you this. It would be nice if you had a piece of graph paper. So get some graph paper, it'll help you. Anyway, so take this data and draw a velocity versus time graph. So pause your video. Okay, we're back. Hopefully you had something like this. So we start out at time equals 0 at 30. Then a second later, it's 20, 10, 0, minus 10, minus 10, 20, minus 30. Okay? Now, does this make sense? You always want to ask yourself that question. Does this make sense? Well, we said that the acceleration is minus 10 meters per second squared. Remember, this is the velocity versus time graph. So the slope is the change in velocity over the change in time. That's acceleration, right? So what's the slope of this thing? I mean, pick any numbers you want, right? The slope of that line is minus 10 meters per second squared. Is that what it's supposed to be? Sure is, right? So it makes sense, okay? It makes sense. Now, what do we call the point time equals 3 seconds? What do we call this? What do we call that? It has a name. It's called a turning point. Why is it called a turning point? Well, two reasons. Number one, the velocity is 0 there. Number two, the velocity before is positive, the velocity after is negative. So a turning point is where the thing stops and it changes direction. So if I had something going this way, slower, stops, then go this way faster, that would be the turning point, right? Where the velocity is 0 and where the thing changes direction. Now, this free fall is incredible. Turning point, yeah. Okay, all right. So I hope you can understand this picture. Okay, so this is the ground. And so I threw the ball at time equals 0, 30 meters per second. So at 1 second, it was going 20 meters per second. 2 seconds, it was going 10. 3 seconds, it was going 0. Now, I didn't want to, so this is coming down. I didn't want to draw it here because it would be too weird looking. Right, so right here again, 3 seconds of velocity 0. 1 second later, minus 10. Another second, minus 20 meters per second. Then here, minus 30. Look at these numbers, will you please? Look at these numbers. What do you notice? There's a lot of symmetry, right? There's a lot of symmetry. So draw a horizontal line here. So how long does it take to go from here to here? 1 second. How long does it take to go from here to here? 1 second. Draw the horizontal line here. Right? So from the ground to where it stops. How long does it take? 3 seconds. How long does it take coming down? 3 seconds. Okay? So symmetry. If I were to draw a horizontal line here, the time from this to this would be the exact same as this to this. So in other words, if somebody told you that it took 5 seconds to, let's say you throw something up, it took 5 seconds to get to the turning point, how long would it be in the air? 10 seconds. Right? Because the time up is the same thing as the time down, so the total time is either twice this or twice that. Something else. What do you notice about the speeds? The speeds are the same. So you draw any horizontal line here, that this time is going to equal this time, the speed is going to equal the speed. The velocities are opposite, right? Because here it's going up, here it's going down. So here, 10 meters per second up. Here, 10 meters per second down. So there's all sorts of symmetries, you know? All right, all sorts of symmetries. So again, you know, if somebody told you that the speed right here was, I don't know, 22, what would be the speed right here? 22, or the velocity would be minus 22 meters per second. So lots and lots of symmetries. You'll use that in some of the problems. All right, here's a great question. So pause your video and figure it out. Okay, we're back. Okay, if you drop an object in the absence of air resistance, it accelerates downward at 9.8 meters per second squared, right? Right. If instead you throw it, what's the acceleration after release? Well, I already did that, right, when I was throwing the ball. After release, you don't have any, you can't exert a force on it. So after you release it, the only force is gravity. And therefore, the acceleration of gravity is what? That, right? Okay, 9.8 meters per second squared. Okay, okay. Pause your video, figure that one out. Okay, we're back. All right, throw a ball straight up. Which of the following graphs represents the motion? Now, again, as soon as you see a question like this, the first thing you want to do is, what kind of graph is it? You know, so you have to notice this is a velocity versus time, right? Velocity versus time. Okay, so you're throwing something up. Well, we just did this, right? You just did this 2 minutes ago. So which one is the correct one? Well, you throw something up, it gets slower, 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 correct? Then it stops, and then it goes faster, 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 faster. This is in the positive direction. This is in the negative direction. So which one is it? And again, wait a second. What's the slope of a velocity versus time? Slope of velocity versus time is acceleration. Acceleration due to gravity is constant, right? Constant. So this can't be it. That's not a constant slope. That's not a constant slope. That's a positive slope. That's wrong because it's negative 10 meters per second squared. So this is the one. Okay, one more. Okay, throw a ball straight up. Which of the following graphs correctly represents the motion? So pause your video and figure it out. Okay, we're back. So this is free fall, right? You throw a ball straight up, it's free fall. What's the acceleration due to free fall? Minus 10 meters per second squared, which is a constant, right? So here, that's wrong. The acceleration doesn't change. This is wrong. Acceleration doesn't change. This is wrong because this has a positive acceleration, right? Here's the time axis. Here's your 0. This is positive. That's wrong. So it's this one. Here's the time axis. That's 0. It's negative, right? Negative 9.8, if you want to be picky, meters per second squared. And by the way, when you do your homework problems, use 9.8. Don't use 10. All right. That is enough for this video. Thank you.